By way of introduction, I should mention I first encountered Michael quite a number of years ago when he came to the lab as part of the summer research program. Oh, I'm supposed to speak English? Anyway, met Michael in the summer research program. At that time, he worked on a project with Professor Megan Huber, and worked in collaboration with another colleague at Northeastern, Dagmar Sternat, working on human movement control things. And I was quite impressed by the fact that Michael, who was an undergraduate at the time, got stuck into this project which had postdocs and all sorts of complicated stuff, but Michael just blithely went ahead. Did very well over the summer. In fact, he did an excellent end of summer presentation. Subsequently joined MIT and joined my lab. But for a while there, I wasn't sure he was ever going to make it out because he kept getting these injuries. He seems to have this fondness for death-wish sports. I think most recently the rugby, is that? Yeah. So rugby is for people that just have no good sense. So trust me, I think about an Ireland, the Irish rugby team is, let's just say, not gentlemen.
But Irish, you like it.
Anyway, so Michael took on a project at the master's level, which he did very well with, and he parlayed that into subsequent work at the PhD level, and that's, I think, what we're going to hear about today. Thank you, Michael.
So thank you guys all for coming, and thank you guys all for coming, and thank you for the warm introduction. So today I'll be talking about my thesis, which is titled "All Models Are Wrong, Simple Models Are Insightful." This is my mantra. Hopefully I'll convince you guys of this by the end of it through a study of human manipulation. So recently there's been increased interest in dexterous manipulation tasks involving contact. And this is shown by the state of the art of robots nowadays. This study conducted at the Toyota Research Institute and Stanford University. And you can see that robots are very quickly learning to do activities of daily living, activities that humans are capable of doing. And they're learning to do these behaviors on, they're learning to do multiple behaviors a day. And what's pushing this work forward is the advancements in machine learning and reinforcement learning, and learning from human demonstration. And they've done a lot of great work in this space to enable robots to do tasks that involve physical interaction. However, these learning methods create what I would consider a bit of a black box between the input and the output relationship. That is, you create a controller and you don't necessarily know when it is going to fail or why it's going to fail. And you may be asking, okay, well, Michael, if these controllers work, well then why does it matter? And I argue having a clear understanding of the relationship between the input and output in your system and having a clear understanding of that controller is important for the subfield of robotics known as prosthetics and rehabilitation robotics. Specifically, if you want to create a prosthetic device that's going to interface with the human and be able to have a controller that's easily interpretable, you should understand the relationship between how humans produce movement, that relationship between the input and the output. Similarly, if someone loses motor function, for example, after stroke, if you want to rehabilitate them, you should be able to have a clear understanding of that relationship between the input and output if you want to rehabilitate them to that relationship. So, with that, the goal of my thesis is to create a descriptive understanding of human manipulation in unimpaired subjects. Another reason for studying humans is what we call the paradox of human performance. When we look at the state of the art of where robots are today, they still pale in comparison to the capabilities of humans. And what makes this paradox even more interesting is when we look at the wetware and hardware of robots and humans. Humans have actuators that are 2 orders of magnitude slower than robots. They have communication that's 6 orders of magnitude slower, and feedback delays that are 2 orders of magnitude greater. So I believe that if we want to bridge this gap between human and robot performance, then we should study human motor control, perception, and learning. Now, humans are complex systems, right? We have greater than 200 degrees of freedom, greater than 600 actuators or muscles. So the question becomes, how can we study these complex systems that humans are? And my approach is via simple models. So the research approach that I take, which we'll talk about today, is collecting what I consider clever experimental data and trying to model the human via simple models and using control theory to create a clear or white box and that relationship between how humans are aiming to produce movement and the result that you see in your behavioral data. So this approach aims to create a bit of a white box in that relationship between the input and the output as opposed to the previous learning methods. Well, this takes me to my thesis, and today I'll be talking about 4 different projects that use that research framework in the previous slide. And I guess I want to highlight that all of these studies are published or about to be published, which is important. So starting with the first study, one key question that I'm going to ask is, can grasping kinematic hand synergies be used to simplify manipulation? And by the end of this section, I'll convince you that no, functional tasks require a different and greater subset of synergies. So you guys are probably sitting there like, Michael, what are synergies? And let me tell you, the synergies are the result of dimensionality reduction. So if we take the equation on the screen, theta equals del as a function of phi, theta may represent your feature space. And if we think about the human hand, that will be relative joint angles of the human hand. Del is a possibly neural command that has fewer dimensions than theta, and phi is a kinematic mapping between the two. So all this is a mathematical way of saying when we control our motion, we rarely ever, we don't control, you can think of it as we don't control each joint individually, rather we control many of them simultaneously. And this has been studied a lot in grasping, and the fact that when people have conducted a study in grasping, they look at a large repertoire of items that you grasp. It's been shown that a few of these synergies, specifically 2 of these synergies, count for about 80% of your hand posture and different grasping tasks. So you can think of these synergies as a subspace of control. You're controlling a lower dimensional space than that is your entire action space or all the joints of your hand. And people have used these synergies specifically in prosthetic and rehabilitation devices. Now, I want to highlight that people have studied these synergies specifically in grasping tasks. And I argue that there's a difference between grasp and manipulation. For example, if you were to pick up a pencil, grasp a pencil, that's not necessarily very useful, but writing with it is, manipulating that pencil is. Think about if you were to pick up a screwdriver. Picking up a screwdriver isn't necessarily very useful, but screwing with it is. You can imagine the motions required for those 2 different tasks are different, which could lead to a different subspace of control or different synergies. So drawing that distinction between reach and grasp, 2 open questions exist in the literature, such as do kinematic synergies emerge in the human hand during functional tool use or manipulation tasks? And if so, are they the same synergies that emerge during reach and grasp of those tools? So I aim to ask and answer this question in the context of an experiment that involved wire harnessing. So for those of you who aren't familiar, wire harnessing is when you have any sort of electromechanical system and you need to provide electricity to it, you have to route cables through the system. And on a manufacturing line, we have a lot of rigid parts or rigid components. That creates a system where you can automate the assembly tasks and use robots. However, when you have a wire harness which is deformable and has complex dynamics, then that becomes a manual task. So this task is a great example of a task that you would like a robot to be able to do, but they can't, so you have a human do it. And also this task involves different aspects of tool use. So specifically what I did was I parsed this experiment into 2 parts. The first part was reach and grasp, where I instructed subjects to reach and grasp an object in front of them. And I measured their hand kinematics using this device called a cyber glove. And then in the second experiment, I instructed subjects to use the tools to install the wire harness on a mock electrical cabinet. And again, I measured their kinematics using a data glove called a cyber glove. So with this data, what I can do is now extract synergies. And the way you can extract synergies is using this mathematical technique known as singular value decomposition, where you set up your data matrix such that you have your different features, in that case our joint displacements in our hand in the columns, and then in the rows we have different timestamp observations of the joints in our hand. So you can think of each column as the time observation of your joint moving. And then after singular value decomposition, what you do is you end up with your right eigenvectors, which are postural synergies. So this is a coordination of how your hand is. So you can think of, in the case of a power grasp, that'll say that you simultaneously flex and extend all of your hands, or all of your joints at the same time. And your left eigenvectors end up being temporal weightings of that posture. So it'll tell you how much you open or close, or how much you project into that coordinated posture. And then your middle matrix is a variance matrix, which tells you how much variance is accounted for within the data, how much variance a given postural synergy accounts for in the data. So with this method, I extracted synergies, and I want to highlight I extracted them in 4 different ways. The first of which is where I took the data from all my reach and grasp tasks and all my manipulation tasks and extracted synergies from the pooled data. And then I wanted to compare just individual reach and grasp of one tool to the manipulation of that tool and extract synergies with just the reach and grasp of that tool and manipulation of that tool, namely the zip tie, scissors, and screwdriver. So what happened, dude? First question was, do synergies emerge? And people look to answer this question by looking at a reduction in the degree of freedom space, the synergistic degree of freedom space. And the way they do that is looking at the VAF, or variance accounted for. And what's shown here is the variance accounted for the 4 different ways I extracted the synergies. And what we see on the x-axis is the synergy order, and the y-axis is the variance accounted for, so how much variance is accounted for in the data by that given synergy. And these lines represent the cumulative variance accounted for, the cumulative sum of these bars. And what we see in gray is the reach and grasp data, and the red and manipulation data. And I want to highlight the glove that I used to measure kinematic data had 23 degrees of freedom, so the maximum number of synergies I can have is 23. However, for graphical reasons, I only show 10, but what's important is that you get a large amount of variance accounted for with a few synergies, 4 or 5 or so. So we do see a reduction in degrees of freedom space. Second thing that you should notice is that when we look at these cumulative variance accounted for curves, in the all-tool zip tie and screwdriver's case, you see a difference in the cumulative variance accounted for between reach and grasp and manipulation. And in fact, what some people do is to quantify this, is they quantify what they call the number of significant synergies, which is often you create a cutoff metric for how many synergies do you need to get a certain cumulative variance accounted for. And one such metric that's been done in the literature is using a cutoff where you have 90% variance accounted for, and adding this additional subsequent synergy does not add an additional 5% variance accounted for. So using these cutoffs, I show here the number of significant synergies with the reach and grasp in gray and the manipulation in red across the 4 different tasks. And after running a 2-way ANOVA, we see a significant effective experiment where specifically we see in the all tools case, the zip tie case, and the screwdriver case, you need more synergies to describe the same amount of data than you do in reach to grasp. But this does not occur in the scissors case, and this is a nice intuitive result. If you think about putting your hand inside a set of scissors, when you put your hand inside a set of scissors, it ultimately constrains your hand, which is why you may see the same number of synergies during reach to grasp manipulation. Now, if you juxtapose that to the screwdriver, you may grasp the screwdriver with the lateral pinch grasp, but when you use it, you involve a lot of finger gating motions, which involves a lot of joint individuation, which ultimately leads to more synergies. So key takeaway from this slide is, yes, we do see a reduction in the degree of freedom space. However, we need more synergies to sufficiently describe manipulation than we do reach to grasp. So the next question was, are reach to grasp synergies and manipulation synergies the same? And one way to answer this question is by looking at the cosine similarity. So cosine similarity is the measure of the angle between 2 vectors, and you can think of synergies as vectors in a hyperspace. So if the vectors are collinear, the angle between them is 0, cosine of 0 is 1. So they have a cosine similarity of 1. The angles are completely orthogonal, they span completely different subspaces, angle between them is 90, cosine of 90 is 0, so cosine similarity is 0. This can be extended to matrix multiplication, where if you have a synergy matrix times another synergy matrix, if and only if these 2 matrices are the same, you'll end up with a cosine similarity matrix that looks like the identity, where you have 1s in the diagonal and 0s everywhere else. So this is exactly what I did, and it's shown here for representative subject, where we see the cosine similarity matrix, where you have 0s denoted by white values and 1s denoted by black values. And what we do not see is that identity matrix. We do not see 1s all on the diagonal and 0s everywhere else. Generally what we see is we see high similarity in these lower order synergies, the first couple, and then as we get to these higher order synergies, 5, 6, 7, 8, the similarity tapers off. And in fact, this trend is consistent across multiple subjects. So what's shown here is the diagonal cosine similarity values, which are termed the similitude, for different subjects, where we see the diagonal cosine similarity as a function of synergy. And what we see is there's a significant decrease in cosine similarity as we get to these higher order synergies. So taking a step back and relating this to the literature, what previously people have shown is that reach to grasp was comprised of a smaller number of synergies, synergies 1, 2, 3, 4, and they discarded the higher order synergies. What I've shown in the manipulation case is that you need, in 2 slides ago, is that you need these higher order synergies to sufficiently describe manipulation. Now, one could say, okay, we can just take the wealth of data that we have in Reach the Grass and apply those higher order synergies. This slide says you cannot do that because these higher order synergies, 5, 6, 7, 8, are different from those from Reach the Grass. So, key takeaway from this section is that synergies exist when the human hand is used to manipulate a tool or complex object. However, manipulation tasks require more synergies to sufficiently describe the motion than Reach the Grass tasks. And Reach the Grass hand synergies and manipulation hand synergies differ, and this difference becomes more pronounced as we get to the higher order synergies. I argue that this work is important for the design of hand and prosthetic devices. If we think about using synergies as a subspace of control, and we think about our action space, we want to give someone a prosthetic device that enables them to do manipulation tasks. Well, if we give them a subspace of control for Reach the Grass, they may not be able to do these manipulation tasks. So the key takeaway is that if we want to restore hand function to those who have lost it, we must study functional hand manipulation beyond just grasping. Okay, so we've talked a little bit something about motion, a way of planning motion. One question you should be asking is, what about force? You can imagine if I'm holding a particular object, let's say my clicker, depending on I can have the same posture, but depending on the force, I may hold or drop that object. So, what about force? Which brings me to the next chapter of my thesis, where I ask a question that's pervasive in human motor control, which is, can humans manage direct force control during motion? And I'll show that no, motion is coupled to force via mechanical impedance. So, in human motor control, there's these competing control theories. The first of which we'll call direct force control, where if you have an applied force, it's purely a function of your planned force. There may be some forward path dynamics that affect this, but your applied force is purely a function of your planned force. And the key hypothesis is, if you have people apply force during motion, errors in contact force will be independent of motion. Now, if this hypothesis turns out to be false, then we propose this indirect force control formulation, where now we have this term which couples motion to force via these interactive dynamics or impedance. Now, two important considerations are that if this indirect force control formulation becomes direct force control under two conditions. If one of 2 conditions are achieved, the first of which is if your interactive dynamics or your impedance is 0, which is found not to be the case of human muscles. And the second is if your input motion and your actual motion are exactly the same. Okay, so with these 2 competing control theories, how did we test them? So what we did was we had subjects sit in front of a robotic manipulandum, and we asked them to apply a constant tangential force in the tangential direction of the robot's motion. So I want to highlight that the robot moved in the horizontal plane, and it moved with a very high stiffness gain, such that if you weren't touching the robot, it was going to move about this elliptical trajectory. If you're applying forces on this robot, it was still going to move about this elliptical trajectory. So the robot was prescribing the motion. Humans were just instructed to apply force onto it. Additionally, we had subjects do this across 5 blocks containing 15 trials, where each trial consisted of 4 cycles about the ellipse. So by the end of this experiment, subjects had gone about the exact same ellipse 300 times. Additionally, we alternated between giving subjects no visual feedback, no visual feedback, and so forth. Where the visual feedback looked like so, where there was a black screen in front of them, where they had a white bar, which represented their target force, and they had a moving red bar, which represented their actual force. Additionally, we had data from a colleague of ours who ran a very similar experiment, but the purpose of their experiment was to answer what was the optimal velocity profile that enabled interaction in this task. And the way they quantified optimal was by instructing subjects to apply 0 newtons of total force. And we were able to obtain this data, which had 10 trials with no visual feedback that matched our conditions. But what they found in their study was that the optimal velocity profile was one that followed the 1/3 power law. And this power law is pervasive in upper limb reaching, where essentially it's the relationship between the tangential velocity and the radius of curvature to the 1/3 power. And just the best way to internalize this is by thinking if you have a curved trajectory, you move faster along the straightaways and slower around the edges. So just to recap, we had subjects move about the exact same ellipse 300 times. They're instructed to apply a constant force in the tangential direction of motion, alternated between giving them visual feedback, no visual feedback, and we gave them the optimal velocity profile. So how did the subjects perform? So what's shown here is a root mean square force error as a function of trial number separated by block, with the visual feedback blocks in purple and the no visual feedback blocks in brown. And what we see in the first case is we do see a significant decrease in subjects' root mean square force error. Subjects reach a plateau after about 9 trials. Now this makes sense. If I were to sit here and ask you guys to apply 5 newtons of force on the table in front of you, you guys would look at me and be like, Michael, what's 5 newtons? But if I give you visual feedback, you'd very quickly start to reduce your error. Now one thing you should start to see is that, okay, they reached a plateau after 9 trials, so these last 200 or so trials, subjects did not further reduce the error, and they still have room to improve. So the question becomes, why were, despite extensive practice, why were subjects not able to reduce their force error? And the reason is force error is motion dependent. So what's shown here is for a representative subject, their force as a function of robot angular position for the 5 different blocks in the 5-minute experiment, where the colored lines represent different trials and the dark line represents the average across those trials. If a subject did this task perfectly, you'd see that they'd move straight at 5 newtons in a straight line. But what you see instead is that subjects are moving in an elliptical or oscillatory trajectory, periodic trajectory. And in fact, we quantified this periodicity using an autocorrelation function, where we found the lag of maximum autocorrelation, and we found that consistently people had these peaks at 180 and 360 degrees. And I want to highlight these peaks were significant, right? We instructed people to apply 5 newtons of force, and consistently you see peaks at 200 newtons. This is a 400% error. So what this suggests is that people are content with a good enough performance which can be achieved using a limited set of primitive oscillations and sufficiently low mechanical impedance. So that's a lot of buzzwords, and I'll explain what that means in just a second. But first I want to highlight that despite extensive practice both with and without visual feedback, subjects did not further reduce their force error in a simple force control task. And that's because errors in force control were motion dependent, which suggests a coupling between motion and force, which can be described by mechanical impedance in our indirect force control formulation. So in the previous slide, I said that a mathematical model combining oscillatory dynamic primitives with mechanical impedance is sufficient to describe this task, and it's also sufficient to describe how humans control physical interaction and their limitations. So you should be asking, what are oscillatory dynamic primitives and mechanical impedance? So in our indirect force control formulation, we have this impedance term, which couples motion to force. And if you think about what we asked, we had subjects apply constant force on an elliptical trajectory. This elliptical trajectory is an oscillatory trajectory in one way that people have hypothesized that you control oscillatory trajectories in human motor control is using primitive oscillations. You can think about that as you fire off a sine or a cosine curve, and you control the phase and amplitude of that curve. So if they've been prescribed to move about an elliptical trajectory, they may plan their motion using a sine or cosine curve, this oscillatory dynamic primitive. Well, if our motion affects our force, then we can start to see why our force is periodic. So I argue this work is important for quantification of human performance and estimation of human intent. For example, if we were to take a step back and think about rehabilitation, this would be a poor rehabilitation task to ask someone who's impaired to do, because unimpaired people can't do this task. Why can't unimpaired people do this task? Well, this study provides a mathematical model to describe the limitations of humans and their force control tasks. So, in the previous section, I motivated the importance of mechanical impedance in what I'm calling the motor action domain, how humans behave. One question becomes, is impedance essential to human motor control, or is it just an artifact of the previous experiment you had run? So, one way to answer this question is looking at the perception domain and asking, can people perceive mechanical impedance? And I'll show that people can perceive an aspect of impedance, namely stiffness, and I'll show that they do so primarily through path information. So, tying together motor action and motor perception, there's this idea in human motor control literature that motor action and motor perception are coupled. One way to think about this is thinking about how babies learn. Babies come out of the womb not knowing how to walk or talk. However, from observing the people in their lives do these, from perceiving the people in their lives do these tasks, they build an internal model of how they can do these tasks on their own. If you think about in the other direction, one way to internalize that is thinking about how if I were not enunciating my words and you were to observe the words I was saying, you'd start to be perceiving how my mouth moves, and from your own internal model of how you would say these words, you'd start to be able to understand what I was saying from reading my lips. So the key question is mechanical impedance part of this motor perception, motor action coupling? We've shown that mechanical impedance is part of the human motor action controller. Can mechanical impedance be perceived? And if so, this implies it's essential to humans' internal model of motor action. So this brings us to our visual perception of stiffness study, where we're motivated by the fact that humans can extract latent information from visual observation of motion. So you can very easily see from these points on the screen, just these dots on the screen move, that someone was walking, jumping, now climbing a set of stairs. A colleague of mine, Professor Huber, was curious and asked, can humans perceive limb stiffness from visual observation of motion? What she did was she had subjects sit in front of a computer screen and observe a two-link manipulator move. She found that yes, people can perceive stiffness, but the question was how. So we hypothesized that people were able to perceive stiffness because the simulated motion that we simulated in these that we use in these simulations were congruent with the human's internal model of the motion. But that didn't answer the question of what motion cues were humans using to estimate stiffness. And one thing that we parse this into is asking the question, is temporal information important, specifically velocity and its derivatives? Recall, in the previous section, we highlighted the importance of this 1/3 power law in the motor action domain. So the question becomes, do manipulations of the velocity profile that violate this 1/3 power law inhibit subjects' ability to estimate stiffness? So how do we test this? We had an experiment where subjects sat in front of a computer screen. They observed a two-link manipulator move, and then rated arm stiffness on a scale from 1 to 7. We had 10 subjects per condition. I'll go over the conditions in just a second, but the subjects watched 30 simulations, which consisted of 6 different joint stiffness values, shown 5 times in block randomized order. So one question you should be asking is, we showed that people were only able to do this task because of the congruency between the control law and how humans produce their own motion. So you should be asking, what is the control law? So the control law is shown here, and the simulation was modeled after the dynamics of an adult male arm moving in the vertical plane subject to gravity under the superposition of 2 impedances, the first of which is an endpoint attractor aiming to pull the hand about a circular trajectory, and the second of which was a joint space attractor pulling the arm to a nominal configuration. And unbeknownst to the subjects, what we were asking them to tease out were changes in this joint space attractor, these changes in these joint stiffness terms. So recall the key question were, what motion cues are humans using to estimate stiffness? Are they using path information, that is displacement, or temporal information, that is its velocities and derivatives? So the way we parsed this out was we ran these simulations, and while keeping the path information the same based off the simulations, so the different paths based off of the different simulated joint stiffnesses here, we manipulated the temporal information, that is the velocity profile. And we did this in a clever way, specifically to violate the power law relationship. And my colleague Megan had 2, in her original condition, you generally followed this 1/3 power law, where you move fast around the straight edges and slow around the curves. Well, in these new conditions, we have a constant condition where your tangential velocity is the same irrespective of your curvature. You have an inverse condition where now you are moving slow around the straight edges and fast around the curves, and the third condition that completely violated the power law relationship. So how do subjects perform? Well, what we see here is that the subject stiffness rating as a function of simulated joint stiffness, and across all the conditions, all the velocity profiles, we see a positive linear effect of simulated joint stiffness on stiffness rating. Now I want to take a step back and highlight these results are quite remarkable. If you think about the task, subjects were just looking at a computer screen, they observed a two-link manipulator move, and they were able to estimate stiffness. Stiffness is inherently the relationship between force and motion. Just from looking at something, you don't have access to force information. So if you think about Hooke's law, F equals kx, people were solving for k using only x. What's shown on the right is individual subject data, and what you can do is you can fit a linear model to this and use the coefficient of determination of this linear model as a proxy of how good subjects were performing in this task. And what's exciting about this study was that our best subject was a physical therapist, and I'll highlight why that's exciting in just a second. So I just want to highlight that we showed that people were able to correctly infer changes in limb stiffness from non-trivial changes in multi-joint motion, which showed that stiffness, or mechanical impedance, is encoded in humans' internal model used to do this task. They can perceive it. We showed in the previous action that it was important in their motor action domain. It must be essential to their internal model. We also showed that they can do this despite manipulations to the velocity profile, which shows that path information predominates temporal information in the visual perception of stiffness. And I think this work has 2 key impacts, the first of which is that we use a perceptual study to learn more about motor action. And I think this is very important from a research perspective because perceptual studies are cheaper and easier to employ. Recall in the previous section when we talked about motor action that required a very expensive robot which must be conducted in lab. This perceptual study only required a laptop, which most of us have, and could be conducted outside of the lab. The second is that it suggests a minimally invasive technique to measure stiffness. So we showed here that people can estimate stiffness using only motion information, which nowadays is quite ubiquitous using cameras. And you can use cameras to get kinematic information using key point detection libraries like MediaPipe or OpenPose. If we can extract and figure out how people are estimating stiffness, this can be important for rehabilitation because when you think about stroke patients, physical therapists talk about patients having an abnormal stiffness, and this is something that they're aiming to rehabilitate. And that's why it's exciting that our best patient, or our best subject in this experiment was a physical therapist. If we can start to extract how they're able to perceive stiffness and quantify subject performance, and we can encode that using kinematic information obtained from cameras, then we can create a system that leads to in-home rehabilitation using low-cost cameras. Okay, so just to recap, what have we learned? We've used a motor perception, we've used a study in the motor perception domain, motor action domain, to confirm the presence of this indirect force control method, which highlights the importance of mechanical impedance, the coupling between motion and force. At the very beginning, we talked about this idea of synergistic motion, where your planned motion in the manipulation space may be planned in different subspaces of control. In this particular section, though, we highlighted that there was a difference between reach and grasp and manipulation. In fact, there was a difference in the synergies across different tasks. These synergies were quite task-dependent, which suggests that you may have more synergies than you do degrees of freedom, and these subspaces of control are something that you develop when you learn different tasks. So this idea leads us to believe that we may have what we call a synergy library, these subspaces of control that we pull from for different tasks that we want to use. Now, from a research perspective, this becomes quite a daunting task. When we want to start to study manipulation, humans are capable of a plethora of manipulation tasks. So how can we start to study a plethora of manipulation tasks? Well, that brings me to the last section of my thesis, where I believe I've created a metric that can help us quantify our study of human manipulation. Specifically this metric called the Variance Accounted For Base Complexity Index. So the key question is, how can we ensure that the tasks we are studying represent the whole spectrum of complex manipulation activities that humans are capable of? And my answer to that question is VAF-CI. So what is VAF-CI? VAF-CI stands for the Variance Accounted For Base Complexity Index. And if you think about our synergies that we talked about at the very beginning, when you extract synergies, you end up with variance accounted for by each synergy, and they come in decreasing order, they're ordered. And with each synergy, you have the cumulative variance accounted for shown by this curve. And the VAF-CI is just the normalized area above this curve. And the logic is as follows, where if you have a more complex task, you're starting to recruit more synergies or more individuated joint motion. Recruiting more synergies would increase the variance accounted for these higher order synergies, which would in turn push down this cumulative variance accounted for curve, which in turn increases the variance accounted the VAF-CI, or variance accounted for base complexity index. So key correlation is that task complexity correlates with VAF-CI. We wanted to test this hypothesis, and specifically test the hypothesis that complexity of 3 distinct tasks can be identified using VAF-CI. So in addition to my studies of reach to grasp and tool use, we ran a study on piano playing. So in that study, we use cameras with MediaPipe to extract the kinematic information from people's hands. And after extracting that information, doing singular value decomposition to extract the variance accounted for the synergies, what we see here is the cumulative variance accounted for across 3 different tasks. And in fact, they increase with complexity in a manner that's intuitive with our understanding. Reach to grasp is simplest, piano playing is most complex. And when we look at this across subjects, what's important is that these differences between reach to grasp, tool use, and piano playing are statistically significantly different. That is, piano playing is more complex than tool use is more complex than reach to grasp. And I want to highlight this metric is better than the current standard that we talked about at the beginning of the talk, the number of significant synergies. Recall, the number of significant synergies, people choose an arbitrary cutoff, whether that be 90% variance accounted for or 80% variance accounted for, and this can specifically affect your results. For instance, using such a 90% cutoff, we see a different number of significant synergies, but when we compare tool use and reach to grasp, we see a statistically different significance between these two tasks. When we change our cutoff to 80%, we do not see a statistically significant difference between tool use and reach to grasp. And this is something that can greatly change the results of your paper or how you interpret the results of your paper, based off of this arbitrarily chosen cutoff, which VAF-CI does not suffer from. Next, I want to say that VAF-CI quantifies manipulation on a spectrum. So what's shown here is the VAF-CI in ordered, where you see the different reach grass tasks and some of the less complex tool use tasks in the lower group. In the middle group, you see tasks that involve more dexterity, namely tying a zip tie or using a screwdriver. In the top group, you see most of the piano playing tasks. And more interestingly, again, I want to highlight this is a spectrum, whereas if we think about the previous slide, the number of significant synergies, that is an integer value. And moreover, when we focus more in on the piano playing task, again, we still see a spectrum. And what's exciting about this is it's consistent with our intuition. One of the pieces with the least complexity according to VAF-CI is that of a beginner level, namely Bach Prelude in C major. And the most complex piece is that of advanced level, namely Chopin's Etude 2511. So, just to summarize the section, VAF-CI can objectively quantify the continuous manipulation of, the continuous complexity of manipulation tasks. And I think this is important for the future of robotics. People, I started this talk by motivating people aim to use imitation learning or behavior cloning to achieve or to improve robot dexterity. So this is the aspect of bio-inspiration. And looking at the state-of-the-art shadow robot hand to solve a Rubik's Cube still pales in comparison to a champion juggler and simultaneously solving a Rubik's Cube in under 3 minutes. I think we can help bridge this gap by using VAF-CI to make sure that we're incorporating a breadth of tasks, incorporating a breadth of complex manipulation tasks that we are studying. And I believe that in the future we should investigate human dexterity through reasonably complex tasks quantified by the VAF-CI metric. So what have we learned? I started off by saying the goal was to create a descriptive understanding of human manipulation in unimpaired subjects. We started off with, we talked about a motor perception study and a motor action study to enforce this idea of indirect force control, which highlights the importance of mechanical impedance. We talked about synergistic motion as a way to simplify the control of dexterous manipulation tasks, but we said that synergistic motion is task dependent, which says there's a lot of tasks that we can start to study. Well, the question becomes, how can we study a complex breadth, or make sure we're studying a breadth of complex tasks? We propose this VAF-CI metric to ensure that. The key contributions to this work is that we demonstrated the importance of studying the human hand during functional manipulation tasks beyond grasping. We developed a controller that competently describes human upper limb force control by describing the limitations in humans' force controller. We identified that human perception of stiffness is dominated by path information, and we developed a metric that can objectively quantify manipulation complexity, which can further the study of human complex manipulation. So at the beginning of the talk, I started with saying that many study dexterous manipulation tasks involving contact via these learning methods. And these learning methods create a bit of a black box because you don't necessarily know the policy that these learning methods develop. You don't fully understand the relationship between the input and output. Now, I propose this metric where we aim to use simple models and experimental data to pull back layers of control theory and how humans produce movement. Now, there's a lot of limitations in my work and a lot of engineering assumptions that we make, but I want to conclude by saying that all models are wrong, but simple models are insightful. Thank you. Before we get to questions, I just want to make a few acknowledgments to a few people. So first, I want to start by acknowledging my mentors who helped me in this trajectory. Specifically, I want to thank you, Professor Hogan. You welcomed me into the lab back in summer 2017 when I was an undergrad, and then I guess I did good enough for you welcoming me back as a grad student. And anyone who knows Professor Hogan knows he's a beacon of knowledge. He knows so much. So I really appreciate the opportunity to have worked under you and absorb some of that. And also I want to highlight for those of you, if for anyone in our lab, we can attest that one great thing about working with Professor Hogan is that oftentimes we go in and meet with him. It's probably because we have a problem, something stressing us out, research isn't working well. And consistently, whenever we come out of those meetings, we come out in a better state, more positive and excited about our work. So I want to thank you for creating such a positive work environment. Next, I want to thank the other members of my committee, Professor Asada, Professor Rodriguez, Professor Venkatesan. Your insights throughout this this proposal, or throughout my research, were very useful, especially in the proposal stage and finishing up. So I thank you again. Lastly, I want to thank some of my other mentors who helped develop me personally and professionally and research-wise. This is a very short list because I knew I wasn't going to be able to list everybody. So for those of you who aren't listed, I'm sorry, but just know you're appreciated. Next, I want to thank the members of the Newman Lab who made coming to work such a great place. Honestly, I feel like we always come to work and we're very happy and it's such a positive environment. I know in 2020, most of us have to work from home. And honestly, I felt like I missed coming into lab, and that's partially because of the environment that you guys created. So thank you for creating a positive work environment, and just I enjoyed being able to come to work and work on particular problems and talk about different ideas with you guys. So thank you for creating such a positive work environment. Next, I want to thank the different diversity, equity, and inclusion initiatives that have helped bring me up throughout my education. I want to specifically highlight NSBE, the National Society of Black Engineers. So for those of you who don't know, the first time I ever learned about a PhD program was at a NSBE conference with my friend Christian here. And we went to this session called the GYM Grad Lab, and it was titled PhD, Why Not Me? And in all honesty, the only reason I went to this session was because I was a broke college student. They had free food. But you know, something stuck, and I absorbed some information, and both Christian and I left and thought, like, hey, we can go to school and we can get paid for it, and we can continue learning. It sounds like a great opportunity. And this ultimately led me to the MIT Summer Research Program, which is what allowed me to intern with Professor Hogan. And the MIT Summer Research Program is a great program that I definitely hold near and dear to my heart, and it creates a space where it allows undergraduate students to learn what it's like to be a PhD student, but also builds them up and gives them the confidence to apply to be a PhD student and feel confident and sell themselves. So I really want to thank MSRP for instilling those values, or giving me that confidence to come up here and say, hey, one day I can get a PhD too. I also want to highlight some of the other diversity, equity, and inclusion initiatives that I've been a part of that have poured into me, not only professionally, but personally. I've participated in quite a few, so I won't highlight all of them, but I just want to say that while we did come here today to talk about my research, these initiatives are what allowed me to pour into my research. I wouldn't have been able to pour into my research if these initiatives didn't pour into me. So I want to thank the people working in these diversity, equity, and inclusion initiatives. I want to applaud you for your work and say it's important and say thank you. Next, I want to thank some of my friends in the different community groups that I was a part of at MIT. First, I want to thank the BGSA and USIM for creating a community outside of lab, especially creating a community of students of color, especially when we think about the times that we went through during undergrad, specifically in that summer of 2020. I want to thank the ACME for creating a space for engineers, minority engineers, to come together and hold each other accountable and talk about our career goals and future aspirations and talk about how we're moving in those directions and call each other out for not moving in those directions and saying, hey, you said you were going to do this and you didn't do that. I think creating those spaces with your friends are very important if you want to move forward. I want to thank the club rugby team for welcoming me to a new sport with open arms and teaching me the game, giving me a space to let out some of my frustrations, and tolerating all my penalties and high tackles for years. Thank you guys. Next, I want to thank my family. I want to start by thanking my brother. When you were born, you have no idea how much it meant to me to be your older brother. A lot of what I do is for you. It's for the ability to make your path a little bit easier. So I really hope that you kind of see me doing some of these things and it instills some values into you to go and move forward in that space. Next, I want to thank my parents, my mom and my dad. For those of you who don't know, I was born right before my mom started medical school. And throughout graduate school, I had a part-time cat, if you will, and there were times where I forgot to come home and feed it. And I can only imagine, the responsibility that it would take to, and the sacrifice it took for you to bring me up coming through medical school. So I want to let you know I really appreciate that, and I love your sacrifices, and thank you. I want to thank both of my parents for instilling the values into me that enabled me to be successful during my research. Specifically want to thank you, Dad, for instilling the values of hard work and discipline within me. That definitely became very important in my research pursuits, specifically around deadline times. But I want to thank both of you guys for instilling the values within me about education and self-love and self-care. It definitely has become true as I've started and grown a little bit into adulthood. You know I didn't always listen as a kid, but you know, I hear a lot of what you guys are saying now, so thank you.
From the cat.
Next, I want to take a second to express a little bit of self-love and a self-gratitude as appreciation for myself. So what we talked about today involved a lot of aspects of you know, the research that I did, and honestly all we talked about were the things that worked, the things that were publishable and created contributions to society. We didn't talk about the different aspects of research that allowed me, or we didn't talk about the different aspects of research where I made mistakes, where I went down the wrong path for months, the moments of self-doubt and the hours of frustration. So I want to just take a moment to thank myself for pursuing and continuing in that hard work, for believing in myself even after I made mistakes, and not giving up on myself in those moments of self-doubt. And just above all, I just want to thank myself for being me, staying true to myself, and loving myself. And last but not least, I want to thank Caroline. So for those of you who don't know, Caroline is the only reason I'm here. In the summer of 2017, I talked to her and I was saying, prior to the summer of 2017, I talked to her and said, I wanted to do these research opportunities at other schools I heard about at NESB. And at the time, I was at home and I was slacking a little bit and didn't apply to any places, and she took the initiative to go and find summer research opportunities for me to apply to. And specifically, she found the MSRP experience, which is what brought me to MIT. And she found this experience, made sure I got my application in on time, and even helped me apply. And she did the same for graduate school. She read my applications and helped me apply, and specifically really encouraged me to come to MIT. So thank you for that encouragement. And also, you've just been an amazing partner throughout my entire time here. And I just want to say that I wouldn't have been able to do it without you. Your love and support has meant everything to me. And I just want to say I thank you and I love you. Thank you.
Seems sacrilegious to go back to the technical aspect. But does anyone have questions? Please, Harry.
So Michael, I congratulate you. You did a great job, and then well, we see the understanding about the manipulations have been, you know, lifted in certain levels. Although you said that all the models are wrong. That's too strong in the words, you know. So you must be a little bit careful about it, but I know you have a very, you know, clear message and philosophy throughout your, you know, research work, which I highly appreciate. I have one question about the you know, last part. You try to quantify the complexity of manipulations by means of you know, synergies, right? You know, the variance analysis, basically. It troubled me a little bit. Let me just tell you some, maybe this would be a counterexample. So, yeah, I have some tools and then do some assembly job. Mm-hmm. Now, the task, I know, I have to place the tip of something to some place. But, you know, this task is not you know, difficult. You can take any postures. As far as the tip is there, you can take any kind of posture. So depending on the individual and depending on the same person, you know, depending on the days or the trial, may take this posture, that posture. Surely it creates the large variations and variability of your data, which is actually misinforming that it's kind of a more complex task. But to me, that's actually very casual. That I can take any stuff and then I can get the, you know, I can accomplish the task, right? So, you know, how do you differentiate? You know, first of all, what is your, you know, rigorous definition of manipulation complexity? What is the definition of that? And then how that one can be applied to such situations where task itself is underdefined or something, you know, you can take some casual, you know, approach.
Mm-hmm. So I guess just to summarize the question, the first question was, what is my definition of complexity? So I would say that this particular study highlights a definition of complexity that is inherently tied to
You have many appreciation slides.
So this definition of complexity has plenty of limitations in itself. It's inherently tied to individuated joint motion. This definition of complexity, where we're looking at the variance accounted for based complexity index. So it doesn't talk about different aspects of complexity that may involve cognitive complexity of a task, or complexity of applying different loads on a particular task, different forces on a particular task. So I would say the definition of complexity that's consistent with the variance accounted for based complexity index is individuated joint motion. Now, the second part of your question asked about if you have a task and there's inherent variance in that task, humans are not repeatable, that will ultimately lead to that task being more complex, which is very true. But I believe, I guess I don't know if I stated it specifically, this variance accounted for based complexity index should be used on like one subset of tasks, not a whole repertoire on that task where you use the data and you've asked people to complete doing that task multiple times.
So if you need more accuracy, more repeatability, it tends to have it tends to be simpler.
I mean,
yeah, you need to do this one in a very repeatable manner. You have to go through it and have to take this one, that tends to be simpler in your definition. Because
So,
having a less variability.
Mm-hmm. So there's I think there's a slight misunderstanding in the fact that, and maybe I didn't explain it well, this variance accounted for based complexity index, you should do it on like one particular task, not the task being done over and over again.
But yeah, one task. However, there's the same task. It's the same task. But someone who is a robot, nervous person, does this job as sometimes going this way, sometimes going that one.
Right. So you'd have.
But how do you train the person? Takes the maybe the optimal the trajectory, right?
Mm-hmm.
So the task is the same, but yeah.
So you're saying two different people, one person who's doing the task, who has more inherent variability when they're doing the task, would be considered more
complex task.
Yeah, it'd be more complex. So yeah, that's a good point. I would highlight that makes an interesting avenue of future research, right? Can this complexity, this variance-based complexity index be used to quantify the difference between novice or expert people, right? Where the expert is someone who's doing something in a more in a manner that doesn't have a lot of variance.
There's some confusion is that the task itself, are you evaluating the task itself or the task execution, which depends on the variability of the task?
I mean, inherently, I'm measuring the task, or I'm measuring the task execution, right? This is a data-driven approach, a data-driven approach, so it's based on the task execution. But I would argue that this method has plenty of limitations, but I think it's a good first step in trying to quantify complexity in manipulation. You just have to understand the limitations in the particular in the metric.
Okay.
Gentleman at the back there.
So I guess somewhat of a related question. So let's imagine whenever you extract one of these synergies, you'd be able to visualize them in some way and kind of observe the actual three-dimensional hand motion that they correspond to. So I'm curious, did you look at kind of any differences that existed like between, let's say, the first synergy across subjects? Like is it that like, everyone uses the same main motion to grasp a screwdriver, or was there something like that?
Yeah, so across a bunch of different tasks, that first synergy is generally what's called a power grasp, where you're just open and closing all your joints at the same time. Now, you can argue that this might be... Oh, sorry, Madhu. The question was your synergies you can essentially Sorry, Nick, can you repeat the question?
Yeah, like when you extract like any given synergy, right? Like you said, think of it as some vector. You can kind of reconstruct it in 3D space and look at what hand motion that corresponds to.
Yeah. So Nick asked, you can view the synergies, and he asked if there was any differences that I observed in the synergies between different tasks. So the answer to that question is, in the first task, generally what you, or in the first synergy across a bunch of tasks, what you generally see is this open close of the hand. You can make the argument that that's honestly kind of, we've designed tools around a hand that opens and closes, and inherently that's what you're pulling out from your data-driven metric. And you get to the higher order synergies. The second synergy, people generally see what's called something closer to a pinch grasp, but it's dominated by this inward thumb rotation. Now, as you get to these the synergies 3 and onward, there's a lot of variability across subjects, even within the same task. Yeah.
Stefan, you had a question?
Yeah, first of all, fantastic talk. I had a question about the visual perception of stiffness. You concluded that people can visually perceive impedance, but you only looked at stiffness. So do you have any idea about if people could visually perceive damping or inertia in the same way, or how you can test that?
So,
Repeat the question.
oh, sorry. The question was, in the visual perception of stiffness task, can people, you said that people conceive stiffness, but you concluded people can perceive mechanical impedance. Can people perceive mass and damping as well? The answer to that question is I do not know. But one way you can test specifically damping is essentially creating a similar experiment where you have people, where you have simulated damping or different joint damping methods. Now, one thing to highlight in that particular study was the conclusion was that people perceive stiffness through path information, right? You know, one hypothesis may be damping is generally related, stiffness is related to displacement, damping is related to velocity. I'd be curious to ask, are people perceiving stiffness, are perceiving damping primarily through velocity information?
Any other questions?
So a little bit, broader, aspect. So understanding, the human manipulation from this the viewpoint. What's your view of how we can actually improve our robotic system?
Yeah. So I mean, I think thinking holistically, I think the learning community is doing it great in the robotic systems. And I think there's even a bit more of a meta question of, do you need to make your robots behave like humans, right? You can ask, for example, a gripper, right? We have our hands, we want to study grasping. Well, one of the best grippers is a suction cup, right? So the question is, the question was, how can this work improve robotic manipulation? I think one aspect where this work can improve robotic manipulation is using simple models as a basis for your learning controllers, right? If you want to incorporate that aspect of anthropomorphism in your controller. If you don't care about anthropomorphism in your controller, then, feel free to continue pushing on with your learning methods.
So how does it inform the way we design the, manipulation and control systems? So you just mimicking that structure?
Yeah, so you can include, so the question was, how do you inform your, how does this work inform your manipulation controller?
Yeah.
And you can essentially include these subspaces of control that were identified from the manipulation task in your controller, right? Rather than giving a prosthetic hand synergies based off of reach to grasp, you can give them synergies based off of manipulation tasks.
Question, Federico?
Well, like in line with the answer
Louder.
in line with the answer you just gave, so what's the limit? So what's the limit of synergies you can have?
Federico asked, what's the limit of synergies you can have? And we just published a paper that says we don't know. So
What argument against this? So why is this a limitation, or is this is this a feature or a bug?
I mean, I would argue that it's a feature. So Federico asked, is synergies a feature or a bug? I'd argue that it's a feature in the fact that you can learn an infinite number of synergies and you can recall on that later on when you're trying to do a particular task. Some people may say it's a bug because it simplifies the control space, and from a robotic standpoint, you lose some aspects of controllability. But you know, that's up to the task and up to the user.
Thank you. Also, a fantastic talk. I think it was brilliant in a lot of ways that I really appreciate. My question kind of falls back to the synergies, and like you talked about wanting to have like a library of synergies. And it sounds like a lot of the synergies also apply across tasks. Like you mentioned the power gripping. Can you talk a little more about kind of like your hopes for using it for rehabilitation? I can see the potential, but I'm curious what you're thinking.
Yeah, so I'm more interested in using it for actually prosthetic devices. So trying to use these subspaces of control. So one thing that you can do is you can design an under-actuated hand in such a system that you may have an actuator that controls one particular synergy, and that synergy will control all the joint degrees of freedom. Now, if you can combine a small number of actuators, then you can create a prosthetic hand that has fewer actuators, which leads it to be smaller and have lower costs.
Thank you.
So as you're describing these synergies and the application as prosthetics and rehabilitation, is there a way to sort of estimate what synergies are kind of not present in current robotics that would seem most important to people? Because I imagine if you've lost action you're familiar with, and it seems like a lot of this is driven on we're trying to get you back to what you're familiar with, the same way visual perception is about your familiarity concept. Are there synergies out there that you're saying, well, that should be an actuator that people need because it's what they're most familiar with, that lets them do this range of complex tasks that you know, that they want?
Yeah, so the question that Nick asked was pushing more towards the application, what synergies are missing that people don't already incorporate in their prosthetic devices? The answer to that question, from my data that I've seen, I believe that individuated joint motion in the thumb, this thumb opposition, could be very important. Oftentimes you end up with a prosthetic that has just power grasp and some aspect of pinching, but I think having this individuated joint motion can enable a lot of manipulation tasks. But I haven't tested that just yet.
Yeah, Michael, great talk. You killed it, obviously, and clearly by the number of questions, you definitely inspired folks about your work. I think one of the things that I like that you pointed out was how the physical therapist, that was one of the most positive results that you received. I'd love to hear you elaborate more about that, and maybe in terms of your future work and some of the things you're thinking about moving forward in research.
So Allegra asks, what is the future work of the visual perception of stiffness and its relation to rehabilitation? So what I'm envisioning moving forward is trying to peel back essentially what exactly is that physical therapist perceiving, how is it correlated to stiffness, and then can we quantify that? So, you know, a big picture vision of what I'd like to see in the future is maybe you have some sort of rehabilitation device that's passive, where people are doing their upper limb reaching tasks on a passive device, and then you can mount a camera on top where you can measure kinematics. That kinematic can perceive aspects of stiffness, which we think is correlated to what physical therapists are using to quantify the rehabilitation. You can send that back to the physical therapist, and they can start to track their patient's progress without their patient coming into the office.
Please.
I was wondering if you could talk a little bit about the potential effect of the kinematic constraints that objects might have in your hand during manipulation, and how the different objects look like you're dealing with a lot of rigid objects, right? And so how might that change, right? These synergies change if I'm now manipulating something that is compliant, and so I no longer have as strict of a constraint, and so would you now have more variability, which would lead to more synergies, or?
So the question that Megan asked was specifically the object dynamics, whether you have compliant objects or rigid objects, how does that affect the resultant synergies? I believe the answer to that question is it really, so the kinematics, the synergies are basically kinematics. The kinematics of your synergies are based on the geometry of the object. Now, what I believe is that you can use what's called a soft synergy model, where your synergy is what you're using to plan the motion. So you're aiming to close your hand, and you just close it blindly, and you compliantly close it blindly such that once you're in contact, the dynamics incorporate that on its own. So I hypothesize that whether you're going to grasp a rigid or a non-rigid object, you're just going to fire off the same synergy, and you're going to let the object dynamics do what they will.
Okay, I don't see a clamor of further questions, so let me suggest we thank Michael again. And now I'd like to go into a private session with faculty and Michael, so anybody who's not faculty, please.
Before you guys leave, let me take a selfie. Thank you guys all for coming. I just want to document this. Thank you guys.
And in addition, so assuming a positive outcome, we will have a brief celebration in, what's the room number?
3434, so it's right upstairs.
One floor up.
Thank you guys.
You explained to